Hello, my name is Andrey Koval. I'll remind you, I'll do another introduction. My name is Andrey. I'm a new postdoc researcher at the psychology department at IALSA and ILabSpan labs. And today is the second installment in the series of COAC Center on Aging Colloquium series dedicated to methods, and in particular R software and R Studio, and also reproducible research. So with that, let me begin. So the second lecture, let's first is going to be on the data manipulation, but let me remind you what we've covered the first time, last time. So the series includes 6 lectures that I've developed. There's going to be also a lecture on latent class and latent transition modeling next week. But the 6 lectures that I've developed, they try to cover the process and skills and tools that are involved in reproducible research and everything else that is involved. So the lectures numbered 1, 2, 3, and 4 constitute a core of this lecture series, during which I will try to demonstrate and explain as I go a reproducible project, a mini reproducible project. So a little to recap. Last time we talked about toolbox and skill set of reproducible research. By toolbox, we mean a collection of software, specifically R, RStudio, and Github. And by skill set of reproducible research, we mean data manipulation, graph production, statistical modeling, and dynamic reporting. We also talked about traditional and reproducible models of research. So this is a traditional model of research in which the data flows through the path of scientific inquiry in a disjoint manner. So for instance, when we need to bring our measured data to the state where it can be analyzed, we use one software. When we need to apply statistical procedures, we use a different software. And when we need to describe the results of these statistical procedures, we use yet another software. In a contrast to that, the model of reproducible research unites those 4 stages of data flow and unites them in a single environment of RStudio that includes both computational and reporting facilities. We said that this path pursues several goals, or reproducible research pursues several goals in a project. So ultimately, we want to answer a research question. However, practically, when we're doing that, we really want to publish something, or write a report, or write a manuscript that somehow encapsulates what we've found, what we've learned. And yet, technically, when we give ourselves technical assignment, okay, this is a time to actually get down and sit down and do stuff, we actually are after producing a dynamic report, because if we can accomplish producing a dynamic report, everything else sort of falls into its place. So today we're going to talk about a very specific area of this pathway of data across the scientific inquiry. And specifically, we'll be after the process of bringing messy data, or various kinds of data, into some order. So we call that order a tidy data. The term invented by Hadley Wickham and described in his paper on tidy data. If you look into the lecture series, lecture slides for this lecture, you will find the reference. Please go read that paper. It's fascinating, apart from being informative. So tidy data is characterized by 3 things, as Hadley Wickham describes. First of all, each variable forms a column. Secondly, each observation forms a row, and each type of observational units forms a table. Well, the third one is a little bit obscure, but it basically means that it's not a database setup, right? So we have a single data set we have, we don't have database connections. Number 1 and 2 seem rather simple, but when you start defining what is a variable and what is an observation, you get into interesting nuances, and this is where the devil hides. So before we begin, I have to announce certain reservations. Well, first of all, the primary focus of this series is on reproducible research, not on learning R, right? R just happens to be there for us to provide a facility to do reproducible research, but if it wasn't for R, we would do it with something else. So there's nothing sacred about RStudio or R, right? Therefore, this is not going to be a core structure to give you as much power in R as possible. My demonstration will be to train, first of all, scientists who want to do accomplish certain objective, don't know how, and they will learn while doing that. So the lecture will be optimized for to have something complete, to have some example complete where you do accomplish certain thing, where you can look back and try to decode what you've covered and learn from that. So I'll be sending you to other and better sources on learning R than my lectures, and I'll keep it to a reproducible research as much as possible, or as much as you need to know R to do that. So goal for today is specifically going and doing that most important step in every project is getting your data in shape, ready to be analyzed, and getting to the point of tidy data. And lastly, this is first part of 4 parts. No dual to get across is let's think in terms of data stages instead of data sets. Now, usually when you start a data science project, at least if I can project from my experience, I would have one data set, and then I would do something with the data set. I'd try to remember what I did with that data set, and I would save it as a different data set. And then something would pass, and I realized that, okay, well, I need slightly different data set that maybe has 1 or 2 different columns, and maybe some other conditions apply to it. And then I create yet a third data set, and so on, while my needs in visualization or modeling continue to accrue. I have more and more needs to produce numerous data sets. Well, what I would like to suggest is to detach from that thinking and think in terms of data stages. So we have a single data set, and we carry the data set through certain stages, through certain steps, en route which we actually accomplish what and we demonstrate what we want to show, right? We take our raw data, and through a series of transformations and manipulations, we arrive at some conclusion that illuminates our answer. So, 3 data stages that I would like to distinguish. One is called, the first called is DS0. This is patient 0 analogy, right? So this is verbatim input from raw files. There's minimum or no processing, and we call it DS0 because we know patient 0, right? So why that's important? Well, if your raw data is stored in some text format that takes a really long time to load it to the memory of the computer, if you do it every time, you might run into some problems time-wise. So what we typically do is if that data is in some remote location, we typically download it once, process it once, and then put it in some more convenient format so we can retrieve it and call it much faster than its traditional format allows. Second data stage is called DSL, and L there stands for long format, or people also refer to it as stacked format. Well, the characteristic of that data stage is that it span of the project. That's an analogy to linear algebra, right? When something that entirely defines the area of interest, or not entirely, but so let's say you have a data set that contains 500 variables. Well, you cannot really work with that data set efficiently if you're working on problems typical in psychology, sociology, behavioral sciences. So typically you do some small subset of that and say, okay, well, I'm studying cognitive aging. Well, let's see what variables that study has relating or possibly can relating to cognitive aging, or something that relating to my study. What can I possibly be interested in that? And I maybe get 20, 30 variables that I'm not sure that I'll use or not, but I sort of keep it a nice, clean data to go for. It's typically a subset of DS0s. It's much more manageable than DS0 and cleaner. It provides context for those focal variables that you study. So if you study cognitive aging, well, probably you want family status, probably you want educational level, probably you want some other things that, although not specifically related to your model, you want to look at in order to maybe anticipate potential confounds in your modeling. And that data stage also invites future research while being relatively stable. Sort of you, in a project, you sort of decide on what you are found after certain tries, establish what the DSL stage should feel and look like, and then you just sort of settle on that and request and work with that for the entirety of your project. And finally, DSM. M stands for model ready. This data stage is used for estimating model and producing graphs. Now, the difference why it deserves a separate name and a separate stage is because when we take the raw information from like experimental information and then bring it to statistical package, of which graphs is a part as well, frequently we would need more information. We would need to create additional variables, dummy variables, for instance, or somehow restructure it, or maybe subset it, or filter it, or do some other minute and very specific manipulations to that particular graph. So let's say you take your DSL and you want to create 3 different graphs. Well, in order to produce those 3 different graphs, you would need to make different alternations to your data set. So instead of creating 3 different data sets, you instead create instructions how those data sets should be created, and store those instructions and operate with those instructions as definitions of a data set. This will become clear as I illustrate this. Important caveat, DSM exists as a query of DSL, so it doesn't really exist on its own. It's defined fully by a query from DSL, and we will always type that query out and give it to the consumer, to the user who reads our reports, so that they will be able to understand exactly what data was selected for this graph. For this project, well, this is general map, right? Where you need to go in general. Of course, every project is going to be very unique, right? So for this particular project, it's real. All the data here is real, and this is not fake. It's not adjusted in any way. But it can work with different levels of complexity. So for this project, I'll have 2 more transitional data stages that will help me keep track of what I'm doing to my data, how I manipulate it, and what process it goes through. So it is stages DSW, and W here stands for wide, and DS long is called long because I want to capture that that data stage is produced always from ds wide. So we take ds wide and we melt it and we produce ds long. And that's what that data stage is for. Now, imagine that if we take a slightly different incoming input file, nothing on this structure changes, right? So we'll still develop code that will go through these data stages. If the input file changes, we don't have to change the code to accommodate that. And that's the benefit for reproducible research. And to complete this map, I've put some typical commands on functions that you would expect to carry out during this stage. So when we take raw files and try to bring them into DS0, we read functions like read.csv or read.rds. When we try to subset DS0 and transform it into DSW, we filter, that is, remove certain observations. We subset it, that is, remove certain variables, columns. We rename columns. We do all other various manipulations with the data set to bring it to that DSW stage. Well, next we got ds long, and DSL is united by this function dscast. And again, this is another function we'll be looking at in our workflow. So you can follow me and work along this this presentation, although this is probably better to be looked at a little bit later so you don't break the focus. But I'll show you how to get there. So if you click on this GitHub link and open it in a new folder, you'll get to the GitHub page that contains all the project files that I've put up for this demonstration. So look at here. It has and contains a bunch of files, and it contains folders. So 3 folders that I do want you to pay attention to and to notice always is data, reports, and scripts. And this is, again, this is not a the organization. This is an organization of a data project that I've came up with. You'll probably come up with your own. So data folder contains data files, no big surprise here, derived and extract. So this is raw file, and this is the file after we've processed the raw. Scripts contains scripts, right? So this is the instructions, code instructions that take those data objects, do something with them, and then put them in a processed folder, right? So this is instructions what to do with data, or with graphs, or just general in terms of utility of this project. So if you want to look at the code in its native environment, you'll have to download zipped archive of this repository, download it, save it, unzip it, and you'll have the ready project file. If you know how to use GitHub, you can clone it in your GitHub client. If you don't know how to do it but would like to know, please talk to me afterwards. Okay, so showed you how to get there. So let us approach our data and get specifically and precise about the data. So the study in the focus that I will demonstrate is Analyst Y97, National Longitudinal Study of Youth, cohort 1997. It's a household sample of US. It has about 9,000 respondents that were sampled by household. It contains 5 cohorts, ages from 13 to 31. Well, that's the longest, the youngest, and the oldest in the current run. It started in 1997 and continues until today. The latest observation was in 2011. And the outcome of interest that we'll be looking at is church attendance, how frequently people attend church. If you would like to involve to see where this data came from, You're welcome to go to Analyst Investigator. I'm not going to cover it here, but here's the detailed instructions, what you need to do in order to recreate the data that I'm starting with. So you can do it on your leisure and then use the code that I developed to inform your future coding projects. So when we download that archive, zipped archive provided by the Analyst study, this is what we get inside of it, right? We got a bunch of files. There's a CSV file you can see. There's DAT file, that's another data file. DCT, that's dictionary used by Stata. Analyst Y97 extension is a tag set, so it contains all the names of the variables that I've downloaded from Analyst Y7. So if you want to use the same variables in their browser, you just upload the tag set and you're ready to construct your own data set. You got SAS file, SPS. Apparently we're not going to use all of it, but in many of these files just duplicate the same information, just in different format, depending on what software people prefer. So apparently we'll use one of these files. So we'll focus on the CSV file and try to work with that. So what I'm starting now is all the code that I'm showing right now is contained in a separate file called DSLR, and it's called so because that script contains instructions for producing that DSL stage, that stable stage that we want to get it before modeling or graphing can process. So let me show you where that file is. If you follow the link, it will direct you to the repository, scripts data, dsl.r, and this is where you have to open it to follow along and adopt the script. So I'll be running some portions of it in here in RStudio as I have it open, but we'll try to follow it on the slides to better see every letters. So in the first section, which you will typically see at the very beginning of many, almost every, I use it in every R document, is a list of packages that your program will be using. A package is an app that go on your RStudio, right? That you have to download and install to carry out a particular function. So as you'll be developing your familiarity with these packages, this screen will tell you a lot what's going on in that project. Next, we would like, and by the way, I forgot to mention this, since this focus is not on R programming, there will be slides that will be skipping over. They are not entirely important, so and you will have time to look over, and I'll be judging it by the time. So sometimes, because this is a completely live code, not every bit of it would be interesting for instructional purposes. But I'll do my best, and we'll see how idealistic I can get about this. So in this line of code, we would like to, first of all, here's our function that actually does stuff, read.scv. And this might be a little bit counterintuitive, but the code is not a piece of text. You don't read it from top to bottom and do it only once. You sort of look at it and see what the keyword is and how to understand and trying to understand the syntax of that. So here, the keyword here is this function read.csv that actually carries out the work we want. Well, it takes in this path source data object, some object that is defined higher. Well, it's defined right here in this line that is defined by some other function as well, paste. Well, paste probably put them together. Okay, so it puts down two objects. One of them is my extract, like this, and another some object in quotation marks. And this my extract is also defined here. So just to demonstrate how to decipher this code, let me switch to RStudio and we'll try to go through it together. Right, so this is what we've done so far. Right, so we ran this code. This was on the previous slide. and it just loaded all the packages. And then we get to this piece of code, and we'd like to run it just line by line. So when we run line 22, we create an object called myExtract, which content is nothing but the string of letters that characterize the address. Well, next we put this myExtract to work by using another function called paste 0, and that 0 stands for 0 spaces in between. So paste 0 will paste everything that is inside parentheses without any spaces between those elements. Can anyone guess what just paste does without paste 0? Right, so if paste 0 concatenates element A and element B, right? Paste 0, if I do that, it does AB. Well, if I do without the 0, what do you think would happen? Just take a guess. You don't have to be right. Just take a guess, develop your intuition, and see if you're right. Okay? So intuition sometimes is going to be more important than knowledge, because you can guess the answer right without even looking around. Okay, so now we've gone to this line 23, right? So it pastes together this myExtract, which we defined before, and this string.csv. So if we run this file, this line 23, we'll get this object path source data that now is a complete file path to the data file. So now we feed it to our rds.csv, right? So we say, this function, go ahead and fetch this file, and we know this file is right here. Header, true, yes, the first row is going to be contain the names of the variables. Skip 0, meaning start reading from the first line, or you can change slightly lower. Separator, comma, if we had semicolon or some other separator with that the data source, the data format uses, we would use that. And finally, on the 25, we say ds0 equal source data, and we basically accomplish our first stage. We got to the point of ds0, right? So we run this, and in our environment tab right here, we see that we have an object called ds0 that contains our information. Okay. As we explore this object, we see that, well, these numbers are not really descriptive. That's a real problem, right? You have to know, you cannot do stuff with the data if you don't know what the data are. So another one way how we can address this problem and find out what those numbers mean and what those column names mean is to go and look in the files that come with extract. So data extract, this is where my extract lives. So in this DTC file, if I open it with just plain text editor, I see, and this is data file, that it contains the data and some space tabulated format, but this top file contains what we need. It contains this automatic number and the description of the variable that comes with the description. So this is useful to us. We can take this and process it to extract those information and use that to rename our variable, right? This is very tedious, and you typically spend a lot of time, and this is when you learn your data. This is when you try to make sure that you can account for every variable in the data. So we got some sex, birthday, what's that? That's month, birth of month. That's year of birth, race, and attendance. Here's our attendance for 12 years. Okay, well, let's return to our presentation and follow the course. So here, what I did is I did very similar thing and read in that file that I've just shown you. But instead of reading the whole file that contains the data, I just read in the head of that contained only the first 17 rows, right? And this is the same thing. I've referenced this file the same way I've referenced the previous one. And this file also contained an extra column, so I removed it. So it contains the column x dot, which was unnecessary. I removed this, and when I printed it out, this file, source labels, now contains this nice automatic file and description. So I use that to rename the automatic variable that, or the computer variable that Analyst Y97, the study, uses it, so that to rename it, rename them in the names that I would like to use. And this is the general structure of a rename command, right? So you simply say your old name, your new name, your old name, your new name, right? It takes two arguments. One is the name of the data set that you would like to rename, and just a bunch of names in that. You can adjust this to your own needs when necessary. Okay, so next I would like to talk about how to query data, that is, how to interact with your data objects. Very simple, just to get you started with R. Basically, I want to talk about three ways. One is to query it with a $sign. So, as in this example shows, this command takes dataset DS0 and selects the column ID and outputs it into a separate object, right? And that object is just a vector, it's an integer, just numbers, right? Well, another way to, again, extract the same information from this database is using square brackets, right? Where the syntax is as follows. So square brackets refer to the tabular reference. So the first element is always going to refer to the rows, and the second will always refer to the columns. So it basically says you put the data object in front of the square bracket, and then you tell what information you want to extract from that data object. So if you omit it, if you leave that argument blank, right, we have to enter the conditions for row and columns in the square brackets. If you leave it blank, it will select everything in the rows. If you leave the columns, the second argument blank, it will leave everything in the columns. If you want to exclude something, or you want to select specifically something, this is when you put something like this. So you say, okay, you see that there is nothing before comma. That's the first argument. That's the conditions for rows. And the second argument, the condition for columns, says ID and sex. Basically, select only columns, columns ID and sex. Okay, so only those two. And this is what this function demonstrates. Okay, the last way to query data is through a package called DeepLiar, and I like this one the most. It is very versatile, but you will want to use all three to really get around. DeepLiar, you have to call it, so load that package into active R session in order to use it, but it has very intuitive syntax. So it uses verbs like filter and select. And filter, intuitively, that's you remove observations. Select, you select columns. So this command will produce all observations in this dataset DS0, which ID number is less than 5. So it retrieves all rows for which ID is less than 5. And it also selects three variables, ID, sex, and race. And this is what we see here. So there's a tutorial. I've created a tutorial on data manipulation specifically and DeepLiar specifically. Browse this tutorial. It actually uses the same data set as I use for these demonstrations, so that should be particularly useful for this case. Okay, so we've arrived at DSW at this point, right? So we said, here's our DS0, we've subset it, we filtered some of it, and now we would like to specify a series of variables that we would like to keep in our DSW, sort of like, okay, we're interested in those variables, let's extract them from our main data object. So we select, first of all, let's see what that does, because this is actually interesting and informative. So right here, I'll run everything preceding to this place in code. And now, let's run this line 83. And that's kind of cool, because look at this. We already know this function called paste0. And it has, again, two arguments. One argument that is this, and another argument that is that. Well, that second argument, if we run it as is, it will return us 12 numbers. It will return a vector size 12. Now, this is a vector of size 12, and this is a vector of size 1. So what's going to happen? Well, we're going to combine a vector of size 1 and a vector of size 12. This is what's going to happen. Okay, so it takes that one stem and it repeats. And this is an example of a vectorized operations in R, and you'll grow to love it, because this is how you speed up many instructions. So now our attend years would now contain the list of values. It's a list of variables that I would like to keep, that I would like to extract from DS0. And also, I would like to select variables ID, sex, race, by year, and by month. So I put these 5 variables and that complex vector into a single object, and then extract those variables from my DS0. So, but now, as I've said, we are arrived at this DSW. Now it's clean. Now it does not have as many variables, and now it has renamed variable names, right? So we have much more convenient data set to work with. Now on to the next stage. Now, as next stage implies, we're going to be converting it to long. But let's look at the data that we'll be doing it to and understand why we need to do this. So this is currently the data that we have. This is the stage of our data set. So it has, let's see, ID, sex, race, by year, a B year, birth year, B month, birth months. Those variables are fine, but these attend 2000, attend 2001, attend 2002, well, the first 5, what, 1, 2, 3, 4, 5 variables, we're taking only once, right? Whereas the next 12, we're taking at specific time points. So what we need to do is actually, we need to have only, well, 6 variables, right? Because we need a variable attend, and then we need the values for that variables for each year. So we will be taking those variable names, attend 2000, attend 2001, attend 2002, and so on, and stacking them into our data set, and we'll show how to do that. Okay, so this is basically how you do it. In this line, ds long reshape to melt, this is where action occurs, right? So this double colon indicates that this function melt is in package reshape 2, right? The first argument typically in a function is a data object. So we know that it takes this DSW and then it does something. The comment on the right says that it melts it, right? So it has, we see two arguments in the melt function, the function that we want to learn how to work with. First is the data object, and the second is this ID vars argument. So we need to understand what that is. And because we also specified this ID vars as important object. So in this case, this ID vars stand for or request for time invariant variables. In other words, or to be more general, it asks for the list of variables that will not be stacked. Okay, so that's an easy verbalization of this rule. And if you ever do melting, you would ask yourself a question. So what does ID vars mean? This is what you need to remember. This is the list of variables that will not be stacked. Okay, so this is what happened. We took this, let's go back one. We see ID, sex, race, by year, and by month. These 5 variables we indicated as those that do not change with time, that are time invariant, and we've indicated that we'd like them to use as ID vars. And this is what happened to our database. Instead of those 12 columns with attend 2000 and 10 2001 and so on, now we have only 2 variables that have stacked the names of the variables in one column and the values of that variable for the other column. Now notice that this is only for person 1. So we would have that stacked for every person in this data set. So if before our data set, let's say, had 100 observations or 100 people, right? So if we had 12 observations or 12 variables that were stacked, what happened to our number of rows? It got multiplied by 12 because for every person we got 12 rows or 11 new rows. Okay. But we've accomplished our goal. So we have, instead of 12 variables that keep track of individual time observation, we have 2 variables that contain the variable name and the value that is also associated with that variable. But now we have a different problem. We have a problem because, in fact, the values of that column called variable contain 2 pieces of information. One is called the name of the variable, and the second is called the time at which that variable was measured. So we need to extract that information, and so we need to do a little bit of editing. What we'll do is we'll create a new variable in this data set called year. And look, you already know this operation. We use a $. So we say DSLong, that's the data stage we're working with. DSLong $year. So it would say, well, go put into that variable whatever value we want, but there is no variable called year in the data set. So we'll create new called year. str_sub, so string subset. It's another function, and there's you don't have to memorize these functions. They will come to you naturally. So don't worry about being overwhelmed with unknown words and functions. This is sort of immersion course. You don't have to understand every word. You just have to. You need to survive and develop some intuition what it might mean. So this str_sub takes the value, looks at this variable column, and takes 4 characters from the end, that -1 from the end, right? And again, it doesn't have to be obvious to you. It just has to make a little sense to you for you to start developing your intuition of our syntax. Right. So we've taken the last 4 characters in the value of that column variable, and we put it into a separate variable column called year. This is what we've accomplished. And once again, we have published all the data for one person. So this is all the data for a single person, and we'll know how many. You know, we have the same thing. We've repeated similar data for similar structure for as many persons we have in the data set. Okay, so we got that, but it's still not enough because, well, we extracted the information from the variable, but it's still, that information is still in the column variable. So we'll have to do a little more editing. We'd like to remove this pattern, and the pattern is, you know, 2000 to 2001. If we have any pattern that starts with underscore and has 2000 or through 2001, we would like that to be removed. And this is what this for loop does. There's other ways to remove it, but I decided to try something else so that you have an example of a working for loop so you can replicate. This forces the values of a year to be a number. This is just an additional data check. And once again, when we print the entire data for a single person, for a person with ID 1, we have what we're looking for. We have, remember that tidy data definition. We have every variable in the column, every observation in a row, and every type of observation in a separate table. Well, we have a single table, we have a single data. So now we don't have, you know, like attend underscore 2000. That was 2 variables in a single column. Now we have only 1. We're good. The data is tidy. So we're arrived at our DS long stage, right? It's not tidy yet, but it's got very, very close. So now what we need to do is to do the reverse, if you will, and it's easier to show what I mean. So let's focus on the difference between these two data sets. Okay, so I'll switch between. Let's try to detect the. So we see that this attend from value of a column variable becomes the name of a variable that contains the value, right? So this is okay. So this is what gets accomplished in this step. So let's see how it's done. So dcast is the reverse of melt, right? So those are 2 opposite functions. So if melt, in melting, we said, here's the set of variables that do not change with time, stack everything else. Here, we do similar thing. We say, here's the list of variables that do not change with time. Here's the variable that changes with time. And here, put the content of that value column that contains the actual value of that variable into the values of a time-varying variable. So we said, okay, ID, sex, race, birth month, and birth year. That's known to us. That's clear because that's time-invariant variables. Here's we add this the variable year that we abstracted that actually keeps the counts, the time. So for it's a little bit trickier to explain it on general example. In case of longitudinal case, remember that you would put all your time-invariant variables first, and then you add your time variant before you tilde it, before the formula closes. So you say, here is what you should keep unstacked. This is what you need to stack, and use the value in the column value right here. If this column was named something else, we would have named it differently. Okay? So now we're almost ready. One last step before we can say that we've successfully created DSL is, well, this is, but we still would like to add a little more touch. So here's the data for variables ID, year of birth, year of measurement, and our outcome, attendance, for a single person, for an ID of 1. Well, what I would like to create is, I would like to create a variable that measures the age of a person at that time point. This is fairly straightforward to do because we have the birth year and the year of that. So if we just take those two, the difference between those two, we'll get the definition of an age. And this is a nice and convenient place to demonstrate how we can DeepLiar to create new variables based on the values of existing ones. There's many ways to do it. DeepLiar is a great place to start because it's very flexible and very powerful. Okay. Final touches to our data sets, and you will have to do this in a real project as this one is you have to assign labels to your factors or to categorical variables, right? So if you get a variable called sex, well, how do you know that 1 stands for female, that 2 stands for male? Maybe it's the other way around. When it's worded properly, when it's like female, so you have a much better chance knowing that 0 is not female and 1 is female. That's good, but not every categorical variable is worded such, and not every database transparent about the naming. So we want to manually assign labels to categorical variables, and you can accomplish it by just putting all that instruction into a separate script. So this is an example how you can call a different script from your main script in R. So let's say you're working on a script on analysis, and that several pages of definitions of what those labels should be don't belong in the main body of your script. So this is an example of what it would look like, and you can go and examine that code for yourself and adapt it for your own examples. Very briefly, you define 2 vectors right here, 2 objects, one that contained actual levels that are possible levels of values, and the other object that contains in the corresponding order what those labels should be, and then unite them in this syntax. It's all outsourced in a separate script. So we've successfully arrived at DSL. Right, so we've filtered, subset, renamed, clean to our DS0 to get to the DSW. Then we melted our DSW to get to the DSLong format that is closer to the tidy data. And then we decasted back again in order to get that nice formation where you get the outcome that you're interested in a single column with a time variable in a separate column. We're almost done. So now that we have this DSL steady and stable, we can say, look, here's the script. We have just done DSL that takes you from step by step how the DSL comes to be. So there's no question. You can go and you can examine that account, how the DSL came to be. So now you have the power to issue a very simple command, something like this, that I show in this block code, that fully define the data that you're using. Right? So it knows that you're starting with a DSL, and everything else is a code from DeepLiar that after some certain use will become very easy to use. So you probably can already intuit from it that it selects only the person. Filter is horizontal, right? Filter selects observations. So it selects only observations for the person with ID 47, and it selects only the columns of ID by year, year, attend, and attend F. And we got this nice, very understood data set. The benefit of that is that you can translate that into this very easily. right? So look, this is exactly one-to-one mapping. You just take the values of attend, you put them on, you put year on a horizontal axis, you put attend on a vertical axis, and here you go. This is our graph. So now we not only see what data goes into producing the graph, we can also print the data in front of every R graph. And we can print the definition of the data in a very handy and small DeepLiar call. And if we have the definition of DSL outsourced in a separate document, that we never have to introduce in our main document, or we can just put in an appendix. We can just operate with only data calls. So you got your definition of in code, how this data set was derived from DSL, unknown data stage. You got data for a single person, so you can understand what the structure of the data is. And you got a visual representation of what that data maps to be. So this is what we're going to do next time. We're going to be looking at how we can map the data that we already know the structure of into visual representation. And when we learn how to model data, how to trying to predict the data, we'll start plotting the models of the observed data that we see, right? That's going to be the lecture after next. So to recap and look forward, we've talked about the path of data in scientific inquiry, and we specifically focused on this little segment that goes from measured data to analytic data. We've said that there's generally you can say that there's a flow between data stages DS0, DSL, and DSM, but every project is unique and probably would require divergences such as this that takes you from to DSW and DS long. Maybe some data set would not require an intermediate step, or maybe require more. So November 4th, we'll talk about producing graphs. November 18th, we'll look at producing models, and we'll keep using the same data set. So if you go and look at it and familiarize yourself, it will be much easier for you in the future. And on November 25th, we'll learn how to put these analyses and discussion and put them into interactive and dynamic documents. And we'll conclude our mini projects that we've started today. And this is everything for today. I thank you for your time. And now, please, if you have any questions, I'll be glad to take them. Oh, yeah, push the button on the microphone when you speak.
Just a reminder to people.
And there's also, we can take questions via email, so please send them to
Anne Greenwood.
At popdata.bc.ca.
Actually, could you put it on your screen?
Yes, that would be. PC.
Andrey, I have a question. I think I'm on. This was a sort of great walkthrough of starting with raw data that may or may not be in a format that you want to use, getting it to the format you want. I noticed you also mentioned the word cleaning the data, which I often find myself spending too much time on. But when I think of cleaning, I think of checking for missing data, checking for errors in the data that have been entered, checking for outliers, other sorts of tasks than we discussed today. Would you say that that's something you would then do once you're at the DSL stage? So in other words, first you have to get the data into a format that's appropriate for your use, and at that point then you would do the cleaning, perhaps in concert with the graphs that we'll do next week?
Unfortunately, no. Unfortunately, you're probably doing data checks along every route, every stage, because there's a particular pitfalls after each transformation. So there's when you melt it, there's something can go wrong, and it would, have some missing data on the IDs or something like that, and then you have something that you cannot figure out. You have to test. You have to make sure that you're expecting data to be numeric and it's categorical, or vice versa, and stuff like that. Yeah, you probably have to build it in at multiple stages, and I think that's good, so that it's easier to localize where the problem is. Yeah, cleaning data is definitely a problematic, and there's not just a single check. You have to check it throughout.
Can you just emphasize again why you would have that extra step from the DS long to the DSL? I'm just trying to understand technically again, because it seems to me they're kind of, you've already represented in a format that...
From DSL to DS long?
Yeah.
Well, there is no step. You usually don't go...
Oh, just so that's...
Yeah, so...
It's DSL.
Actually... Okay. So once you get to DSL, like sometimes production of certain graph would ask you to transform the data for which you use melting and casting as well. And that's why I was trying to always correct myself, saying that it doesn't relate only to longitudinal cases where you can easily conceptualize it. Oh, well, that's time variant and that's time invariant variables. It's clear enough for me to see. It's a little bit more complicated than that I didn't want to spend time, in a single lecture. So what typically happens is you arrive at this, at some stable stage, and then you sort of create that as a reference point, so that you can say, okay, so 2 steps from this reference point, I'm in this place. 3 steps from that reference point, I'm in this place. 5 steps from this reference point, I'm in this place. Ideally, we want this place to be as close to those potential points as possible. It's never going to happen. We always have to sort of little adjust. What typically happens, you get to this DSL stage where everything is nice, everything is tidy, but then you realize that, well, actually for a different graph that actually treats that variable as actually flips over and does the dummy thing, or does something weird to that and reformats the structure of the data because it asks for different data to portray it. You would start, you would have to redefine variables in your own case and observation in your case and see how that, what adjustments you have to make in these formulas to accommodate that. I wish there was a simple answer saying, use this data for, line graphs. There's no easy answer to that.
There was a question, just maybe not everybody attended the first session, a reference to the site, the IALSA site that you'll be using for resources and things in the future. So maybe just a reminder for people who have registered today.
So the easiest way probably is to go type in IALSA tutorials in Google, and I think that's the first link that comes up. So IALSA tutorials, yeah, and it's right here. So IALSA github.io/tutorials, or easier, Google IALSA tutorial and the first lecture. So that site is still in development, and that's good because you always want to have a site that is in development rather than already has all the content. That's the best rationalization for not doing it yet I have. So, yeah.
And that will let me in?
What?
It will let me in? It's open to the public?
Yes,
okay.
Absolutely, yes. It's all public domain. So, yeah, I will be creating a data knowledge for IALSA lab here based on these lectures, and these lectures are loosely based on this knowledge base. So it's a nice synergy, and I'll be developing this resource, so check for updates. Get better. Thank you. Well, thank you.
Oh, I have a question.
All right.
Of course. Wanted to find out if the coding
Button.
Sorry, thank you. Just remind other people, not myself. Just a question, and I think we've answered it, but I wanted to find out if the coding and/or the presentation could be posted or sent to participants. So that's, you would have those things posted on this site?
As I mentioned at the beginning, you can go in my presentation. If you go to IALSA tutorials, and you on the front page, there's a link to the Colloquium series. The Colloquium series has the same information that you would get from the flyer, but it also has the active links to these lectures. So, and these will stay there for as long as that site stays. And that loads individual presentations, so you can always go back and look at it. Also, if you go to this GitHub button, you can download the entire content of this presentation that I did, both as a DSL a script, and also what I would encourage you to look at is the overall structure of this repository, of this project, because this is how RStudio will think. It's not going to think about it in a single code, in a single script. It will think as a collection of files and folders. If you want to just look at the code, go to this download zip on this page, and yeah, just download it and unzip it, and it will contain this exact folder that you have here, and you'll have all the scripts and initial data sets and everything that I've referred to during the lecture. Oh, and this is what I did when I was learning. I would just copy whoever's repository project and try to understand whether those concepts made sense. And if they did, I left it. And if they didn't make sense, I created my own. So it's sort of, you always have to do it. So yeah, great question. Thanks.
Thank you, Andrey. I'd just like to, make a personal note of thanks for all the resources that you're providing to everyone, as well as the PowerPoints. And did want to add that we are recording these sessions, and we have a link for the first sessions that we can provide you with. And this session and future sessions will also be recorded, so we'll be providing links to people. If you're in the registration system now, then you'll be getting reminder emails from the Center on Aging in terms of the next session and resources and links as well. So anybody who's lost the registration link and things like that will be assisting that way. So thank you very much.
Thank you. Have a nice day.